Hi everyone, and welcome to our lecture on Data Analysis Part 1. In this video, we'll explore different types of data analysis and how they help us make sense of information. We'll also review data aggregation, which means combining and summarizing data and interpretation metrics, which are the numbers we use to understand what the data is telling us. By the end of this session, you'll have a better grasp of how to turn raw data into insights. Let's dive in. So, what exactly is data analysis? It's the process of examining, cleaning, transforming, and interpreting data in order to find useful insights, draw conclusions, and make better decisions. Think of it like being a detective, except you're working with numbers instead of clues. The process usually involves a few key steps: collecting data from sources like surveys, sensors, or databases, cleaning the data, fixing errors, handling missing values, and ensuring consistency, exploring the data to understand patterns and relationships, analyzing it using statistical or computational methods, and finally, interpreting the results so we can make informed decisions. For example, let's say a coffee shop owner wants to know their busiest day. They collect daily customer data, clean it, and analyze it. The result? Fridays, especially afternoons, are the peak times. So they decide to schedule more staff on Fridays. That's a great example of using data analysis to drive smarter business choices. There are 5 main types of data analysis: descriptive analysis, diagnostic analysis, hypothesis, testing, predictive analysis, prescriptive analysis. We usually start with the first 2, descriptive and diagnostic, which together form exploratory analysis. This helps us understand what happened and why. Once we've explored the data, we move on to hypothesis testing to see if our observations hold up statistically. Then, predictive analysis helps us look ahead, and prescriptive analysis tells us what actions to take based on those predictions. So overall, it's a journey from exploring the data to making data-driven decisions. Descriptive analysis helps answer what happened or what's going on. It summarizes and simplifies past data to give us a clear overview of trends and performance. This type of analysis uses numerical statistics like averages, totals, percentages, and counts, or visualizations like charts, graphs, and summary tables. For example, a company reviews last quarter's sales to see which products did best and which regions performed the strongest. Descriptive analysis provides that snapshot and helps them understand their recent results. Descriptive analysis tells us what happened, but sometimes that's not enough. When something looks unusual or unexpected, we use diagnostic analysis to figure out why. It's about asking, why did this happen? Or what are the causes of past results? And identifying the root causes. It often involves drill downs, data mining, correlation analysis. For example, sales dropped last month. Diagnostic analysis helps uncover possible reasons, maybe a failed ad campaign, a supply issue, or changing customer preferences. So diagnostic analysis goes beyond just seeing the numbers, it explains them. A hypothesis is basically a question we want to test using data. We often form hypotheses after exploring patterns, and hypothesis testing helps us check if those patterns are real or just due to chance. The whole process involves 4 steps. Step 1, set up the hypotheses. We begin with a null hypothesis, H as 0, which assumes there's no real difference or relationship. It's like the default assumption. Then we have an alternative hypothesis, HA, which is what we want to test. It reflects what we think might be true based on our earlier observations or questions. Step 2, decide on a significance level, alpha. Alpha is the cutoff we choose, usually 0.05, to decide how strong the evidence needs to be before we're confident in our result. It reflects how much uncertainty we're willing to accept. Step 3. Calculate the test statistic and the p-value. We run a statistical test that gives us a test statistic, a number that tells us how different the groups or values are. From this, we get a p-value, which tells us how likely we would see this result if the null hypothesis were actually true. Step 4. Draw a conclusion. If the p-value is greater than alpha, we fail to reject the null hypothesis, meaning the result isn't strong enough to be considered significant. If the p-value is less than or equal to alpha, we reject the null hypothesis, suggesting that the result is statistically significant and supports our alternative explanation. So, to sum it up, hypothesis testing is a formal way to test the questions we come up with during our analysis. It helps us decide whether the patterns we see are likely real or just due to random chance. Now, let's move into predictive analysis, which is one of the most exciting types of data analysis. This is where we take the patterns we've found in past data and use them to forecast what might happen in the future. It's like having a crystal ball, but powered by statistics and machine learning. Predictive analysis is all about answering questions like, what's likely to happen next? If this trend continues, what should we expect? Who is most likely to respond to our offer? We use tools such as regression models, decision trees, or machine learning algorithms to build these predictions. The models look at historical data, learn from it, and then apply that learning to new or unseen data. For example, a retail store wants to prepare for the upcoming holiday season. They look at data from the past 5 years and notice that toy sales spike in late November and early December. Using predictive models, they estimate which items will be most popular this year based on current trends and past behavior. With that forecast, they can order inventory ahead of time and plan promotions to match demand. So predictive analysis helps businesses and many other fields anticipate the future and make proactive, data-informed decisions. Once we can predict what's likely to happen, the next step is prescriptive analysis. This type of analysis doesn't just forecast the future, it recommends what we should do about it. Prescriptive analysis helps answer questions like, what's the best way forward? Given these possibilities, what action will give us the best result? How do we optimize our resources or outcomes? It uses advanced tools like optimization algorithms, simulations, and machine learning, often factoring in constraints such as limited staff time or budget. Imagine a delivery company expects high demand next week. Their predictive model forecasts a 30% increase in package volume across the Midwest. Prescriptive analytics then steps in to help them decide how to respond. It might suggest hiring 5 temporary drivers, rerouting deliveries to reduce fuel costs, and starting shifts earlier to avoid traffic. Prescriptive analysis is powerful in logistics, finance, marketing, and healthcare, any area where you not only want to know what might happen, but also what actions will produce the best results. Before we move further, let's clarify 2 terms you'll hear a lot in data analysis: data aggregation and interpretation metrics. They're related but serve different purposes. Data aggregation means combining or summarizing data so that we can better understand the big picture. It's a way of reducing complexity. You might group the data by region, by time period, or by customer segment, and then summarize it using functions like total sales, average rating, or number of orders. For example, adding up daily sales to calculate monthly revenue. Instead of looking at 30 rows of daily data, you now have 1 row per month, much easier to work with. On the other hand, interpretation metrics are the numbers we use to evaluate or explain performance, behavior, or trends. These metrics often come from aggregated data, and they help answer the question, what does this mean? For example, the conversion rate, the percentage of website visitors who make a purchase. This tells you how well your site is turning visitors into customers. In short, aggregation simplifies and prepares data. Interpretation metrics help explain or evaluate what the data is telling you. Let's now talk about 3 basic but powerful techniques: searching, filtering, and finding unique values. These are often the first tools we use when exploring a dataset, and they help with both aggregation and interpretation. Searching lets you find specific data points quickly. For example, if you're working with a customer database and want to find all sales made by John Smith, searching gets you those rows instantly. Before aggregating, we might search for all orders from a specific city, like Columbus, so we only summarize the relevant data. Filtering means narrowing your data down to rows that meet specific conditions. Let's say you have a large spreadsheet of transactions. You might filter it to only show orders over $100 or to only include sales from the month of June. This helps you focus on a specific part of the data, maybe to calculate average order value or see trends in a certain region. Unique values show all the distinct entries in a column. This gives you a sense of how diverse the data is. For example, if you check the state column and see 50 unique values, that means your sales span all US states. It also helps spot problems, like if New York shows up as NY and N.Y. You might have inconsistent entries to fix. These 3 tools, searching, filtering, and unique values, are essential for understanding and preparing your data before deeper analysis. Now let's talk about aggregate functions. These are the building blocks of summarizing data. These functions help us move from looking at individual data points to understanding the overall story. Let's look at 4 of the most common. Sum adds all the values in a column, imaging that you're running 3 coffee shops and want to know how much total revenue you made in March. You'd use sum sales to get that one big number. Count tells you how many records or entries exist. For example, if each row in your spreadsheet represents an online order, count order ID gives you the total number of orders placed. Very useful for reporting or tracking volume. Max and min show the largest and smallest values. For instance, let's say you want to know your highest and lowest sales days. Max sales might show your record-breaking day, $5,200. Min sales might show a slow day with just $240. These functions are simple but powerful. They help you understand scale, range, and performance at a glance. Let's continue with 4 more aggregate functions. These are especially helpful when you want to understand how your data is distributed. The first 3 are central tendency measures: mean, mode, and median. And the last one is a spread measure, standard deviation. Average, or mean, gives you the average value. For example, a school wants to know how students did on a test. If the total score from 100 students is 7,800, then average score is 78. This gives a quick picture of overall performance. Mode tells you the most frequent value in a column. For example, you run a customer satisfaction survey with ratings from 1 to 5. If most people gave a score of 4, then mode equals 4. This tells you what customers are most commonly experiencing. Median is the middle value when the data is sorted. For example, if household incomes are all over the place, from $20,000 to $1 million, the median helps avoid being skewed by extreme values. It shows what a typical household earns. Standard deviation tells you how spread out the data is from the average. For example, 2 classes have the same average test score, say 75. But in one class, everyone scored between 73 and 77, while in the other, scores range from 40 to 100. The first class has a small standard deviation, more consistent. The second has a large standard deviation, more variation. These functions help you summarize, compare, and understand variation in your data, and they're used in nearly every kind of analysis.